All right, class, welcome to section 3.3. We will be discussing graphing quadratic functions and then looking at some of their applications. So we're finishing up the chapter on quadratics by discussing the quadratic functions. We definitely looked at the graph of a quadratic function since chapter 1. We've use transformations to graph quadratic functions, and then we want to take another extra deep look, if you want to call it, like a little paying more attention to quadratic functions and see what else is happening. So number one, quadratic function is got its toolkit function as f of x equals to x squared. So let me graph it one more time for you. If you plug in some of the values into this function, if you plug in a 0, 0 squared is 0. If you plug in a 1, 1 squared is 1. If you plug in a negative 1, negative 1 squared is also 1. And then let's see about 2 and negative 2. Of course, if you square both these values, you're going to produce a 4. So as you see, the graph of the quadratic function is very much symmetrical about the y-axis. In other words, it looks the same on the right side as it does on the left side of the y-axis. If you reflect this function over the y-axis, it looks exactly the same. So therefore, the quadratic function is an even function. The graph of any quadratic function is called a parabola. So far in this course, we've learned to deal with linear functions. Their graphs were lines, right? We've learned to deal with absolute value functions. Their graphs were shaped like a V. And now we're learning to graph quadratic functions. Their graphs are shaped like a U-looking thing, but we call this shape a parabola, okay? So moving on through all our functions. Now, here are the characteristics of a parabola. So anytime we graph a quadratic function, and by the way, what makes a function quadratic? Well, the same what made everything else in this chapter quadratic. The fact that we will see an x squared, right? So the highest exponent of your variable is going to be a 2, and it has to be there. That's why I'm saying a cannot equal to 0, yes? So the highest exponent of your variable is a 2, and you have to see it. So whenever we will graph a quadratic function, again, its shape is going to be a parabola. There's a very pretty parabola for you. Most important piece of a parabola, same as most important piece of the absolute value function, is that turning point. So right here, the turning point in the parabola is called a vertex. So anytime we draw a parabola, we have to have the vertex. We have to know where we can turn this parabola. Okay. Now, it is also important to know that the graph is symmetrical about this vertical line that goes through the vertex. So in other words, the graph looks the same on the right side as it does on the left side of the graph. Okay. Now, of course, for our quadratic function, our toolkit function, the vertex is in the origin. Whoops, I didn't mean for me to erase everything. So the vertex... What? Oh, okay. Sorry about that. The vertex is right here in the origin, right? Okay, and then we already said that the y-axis is our axis of symmetry. So in other words, the parabola looks exactly the same on the right side as it does on the left side of the y-axis. But of course, as it happens with any other, like all the linear functions just had the shape of a line, but they're somewhere else on the plane. We have graphed absolute value functions, right? They look just like the absolute value graph, but somewhere else on the plane, right? We shifted it up and down and left and right. We made it narrower. So same thing with the parabola. Wherever we're going to move this parabola, the vertex comes along somewhere. Yes, move somewhere along. The axis of symmetry is still going to go halfway through the parabola, right? Through the vertex, and the graph will look exactly the same, will open the same way left and right of this axis of symmetry. Many times we could find intercepts. So many times, same as we drew lines, the easiest points to find on a graph are the intercepts. Again, make x equal to 0, find the y. Make y equal to 0, find the x, right? So if you're on the x-axis, the y's are 0. If you are on the y-axis, the x is 0. Okay, so again, these are features that we might be looking for whenever we graph a parabola. So also want to remind you from the past, when we looked at the linear equation in two variables, linear, right? So x was to the power of 1. We had the ax plus by equals to c as our general form of a linear equation in two variables. However, a much better form of it was the one where we had it solved for y. Okay, so we call this the slope-intercept form. And so this was very nice because if I have the equation of the line in this form, I already have a point, the y-axis intercept, and I know how the line is moving, right? So I have the slope, so I know how tilted the line is. So the same way with the quadratic function, we have our general form right here. Most quadratic functions will be given in that form. However, this can be modified. Same as here, we can solve simply for y, and then we have the equation in slope-intercept form. Same thing, we can modify the general form of a quadratic function into this format of it. Again, we can factor out the a. It's called completing the square method that gets us there. So we can do some factoring, things like that, and put the equation in this format. And if we do have it in this format, it's much, much easier because then, according to this form, which by the way, we call it the standard form of a quadratic function, in this format, this value hk, these numbers hk, are actually the vertex of the parabola. Okay, and that's important because remember what I said, if you want to graph a parabola, you have to know where its vertex is. Yes. And so because this format gives us the vertex of the parabola, we also call this the vertex form of a quadratic function. Much better because we know, oh, that's the form that we have the vertex given for. Okay. Now, if the quadratic function comes to us in this format, then of course the axis of symmetry will be the line, the vertical line crossing through the vertex. And so, of course, a vertical line always has equation x equals to number. That number is going to be h. Now, if this value a is positive, then the parabola will open up. And this value a is negative, then the parabola opens down. So we actually have quite a bit of information. Not only that, we would also know how wide the parabola is based on this a value. So I just want to graph a few quadratic functions. We will graph them using transformations. And I just want to show you how both these next graphs are going to be given to us in standard form or simply called vertex form. And I want to show you how indeed these numbers hk happen to be our vertex. So let's pretend we don't know what format this is. And we simply need to graph this quadratic function using transformation. So what are my steps? Number one, as we did in chapter 1, identify what the toolkit function is. So what type of a function is this? So I know what shape to start with. So because I see the square, the x squared is my toolkit function. So that's what I start with. So just as we did before, it goes through 0, 0, 1, 1, 2, 4. And then the same way on the other side. Okay, so what kind of transformations do we have? Number 1, I'm looking at the x transformation. So in that parentheses, before I see the square, I see an x plus 2. So therefore, my parabola is going to move 2 units to the left. So all my points are going to move 2 units to the left. Now remember, because again, we're doing the opposite, right, of what it says. So here you have it. Okay. All right. What else? I see a 3 multiplied to this parentheses and then minus 4. Of course, y transformations have to be performed in the order of operation, so I'm going to do the multiplication by 3 first. Now 3 times all the y's from before means exactly that. Take all these y coordinates and multiply them by 3. So this point here has a y coordinate of 0 times 3 is still a 0. This y coordinate here is a 1. I'm going to multiply by 3, so it moves up to 3. So this y coordinate here is a 4. If I multiply by 3, it's going to go to 12. That's going to go way up there. I have no room for. But the point is, as you see, this graph got stretched vertically by a factor of 3. So it's where it's at. It just got stretched vertically by a factor of 3. Okay, and the last and final transformation is that I have a minus 4 subtracted from this function. So I'm taking the green graph from before, right, all those y values from before, and now I'm minusing 4 from them. So that simply means the graph is going to move down 4 units. So it's keeping its very stretchy shape, but it's moving down 4 units. Okay, so there it is. That's the final answer. So if I look at this final answer, could you tell me where is the vertex of this parabola? The vertex is this turning point. I'm looking to the x-axis and I see a negative 2. I'm looking to the y-axis and I see a negative 4. So just as you see right here, and it's the opposite, right? So see how in this equation here it says x minus h? So the vertex is at what's subtracted from x. And in here, what's subtracted from x is a negative 2. Therefore, minus minus 2 gives you the plus 2. So the x-coordinate of the vertex is negative 2. That's what's being subtracted from x. And then the k, the y-coordinate of the vertex, is what is being added back here. And what's being added is a negative 4. So exactly as you see why the vertex is there, because, again, to draw this function using transformations, we have to go 2 units left. So therefore, it moves from 0, 0 to negative 2 for the x. And then 4 units down. So we're going down to negative 4. So that's our vertex. All right, this a value at the front is positive. So therefore, we didn't have to flip the graph about the x-axis. So our parabola is still oriented up. In other words, opens up. But that value 3 kind of, it's not a slope, but it kind of tells you how the graph is going to be moving to this first point, right? So a regular parabola goes from 0, 0 to see the A value here at the front is a 1, so I'm going 1 right, 1 up. And again, I'm not drawing a line. I'm making still a parabola, but that tells me how wide the parabola is opening. This 3 value, right away I'm going 1 unit to the right and 3 units up, and that's exactly where I find my next point. Yes. So that tells me, and of course symmetrically on the other side, I get this point here. So that tells you exactly how narrow the parabola is going to be, right? How fast the parabola goes up or down. Now that we have the vertex, can you also tell me what's the equation of the axis of symmetry? And the axis of symmetry is this vertical line that goes through the vertex. So right here, that's the axis of symmetry. So as such, being a vertical line has equation x equals the x coordinate of the vertex, so -2, right, as you see. We can even read the domain and the range of the graph, so I'll take this aside. This is going to be part of questions you will need to answer for a test, so, and also for homework. The domain is all real numbers, as the graph will slowly but surely stretch all the way left and all the way right. But the range becomes interesting in quadratic functions because this parabola opens only from one y value up, as in this case, or maybe if it opens down, then it's just going to go down to -infinity. But as you see, this value in the range has to do with the y coordinate of the vertex. Okay, and then of course the parabola opens up, it goes up to infinity. If it opened down, it would go to -infinity. All right, so let's try this one more time using transformations. Or this time it says, now that you are hopefully convinced that this is how the graph is moving, let's just not even have to go through all the steps of the transformations unless you want to, no problem. But can you tell me where the vertex is? So hopefully you're convinced that the vertex is what's being subtracted from x and what's being added back behind the quadratic. So that's my HK. So in other words, this parabola is going to turn at 3, 2. Yes. But we do not know where it's turning to. So, for example, what I could do is like I need to know how wide this parabola is opening. So I can look at this A value here. Now, the fact that A is a -1/2, that simply means the parabola opens down, because A is a negative value. And because of all the transformations, somewhere we would have had to flip the parabola about the x-axis. But it just says you just use 2 more points, right? So easy enough. What I could do is I could plug, the vertex is at 3. Yes, x is 3. So just figure out 2 more points left and right of it. You really don't need any more points. So more than one, just 1 more point is going to be enough. So I'm just going to see what happens if x is 4. I'll start there. So if x is 4, what is f of 4? Okay, so that's -1/2. 4 minus 3 squared plus 2. So all I have to do is just plug this into the calculator. That's a 1, so that's -1/2 times 1 plus 2. That's going to be a 1.5. Okay, so here it is. If x is 4, y is 1.5. And that's really all I need, because we know that this parabola is going to be symmetrical about the line that goes through its vertex. So therefore, this point to the left of it is exactly the same, It's exactly the same way. Oh my gosh, I just put in the red. Okay. So now we know how wide this parabola is. Okay. You can find another point if you want, but you don't have to. But also remember what I said about this A value. It's again, not a slope, but it's like a slope. So in the previous problem, A was 3. So then all I had to do is from the vertex, go 1 unit to the right and then 3 units up. Yes, and then the same way symmetrically on the left side. Here, A is negative 1/2. So in other words, I'm going to go 1 unit to the right and then just half of unit down because it's a negative. And therefore, that's exactly how we found this point. And then symmetrically on the other side. So that's how my parabola opens. Now, of course, the axis of symmetry is the line x equals to 3. And of course, the domain is always all real numbers, but the range, as you see, goes from negative infinity up to this highest y value of 2, right? So that's the highest point on the graph is at 2. Then it goes all the way to negative infinity, except for we always have to go from smallest up to largest value. So from negative infinity up to 2. All right, so it is very helpful if the equation of the quadratic function is in standard form, or in other words, in vertex form. If we do have the vertex, as I said, it's kind of like in a linear function or a linear equation in 2 variables. If I could have it in slope-intercept form, I immediately can find the graph because I have a point, the y-axis intercept, and then I know how my line is moving with the slope. So the same idea here. If I know the vertex, so specifically this point on the graph, and I know how my line is moving, in other words, what the A value is, then pretty much I have the graph of the quadratic function without any delay. Okay, and by the way, I very much I very strongly recommend that you put this quadratic function in your graphing calculators, put it in Desmos or your graphing calculator or your graphing app, and see and verify again that indeed the graph is what we got. Okay, so it is very helpful if the equation is in standard form because we would know the vertex. If the equation given is in general form, then we do not know what the vertex looks like, right? However, we can easily do so if we use this formula here. So if an equation is in general form, then here is how we can find the vertex. The x-coordinate of the vertex is negative b over 2a. And the y-coordinate of the vertex is always how you find any y to any point. You plug in the x value into the function, and you're going to get the y value to it. Okay, so we'll practice in a minute. I do want to show you that the x-coordinate of the vertex is really just the, if you remember the quadratic formula, negative b plus or minus the square root of b squared minus 4ac divided by 2a. So the x-coordinate of the vertex is this piece of the quadratic formula where you don't see the radical in it. Okay, so because the square root, basically what happens at the vertex, the quantity inside the square root becomes 0. So it's, if you have learned the quadratic formula, great. You will also know what the vertex formula is because it's just this piece of it from the quadratic formula. So let's use it. Here is a quadratic function in general form. It says find the vertex. Great. and then rewrite the function in standard form. Okay. So the formula above says that the x-coordinate of the vertex, which we've been calling h, is simply negative b over 2a. And for us, b is negative 6, a is 3. Okay, so again, minus is part of the formula. B itself is a negative, and then over 2a. So minus minus is a plus. 6 divided by 6 is 1. So the x-coordinate of the vertex is 1. Easily done. The y-coordinate of the vertex, as I was saying before, to find the y-coordinate of any point given an x, all you have to do is plug in the x into the function. And that's how you easily find your y. So 3 times 1 is 3. 3 minus 6 is negative 3. Plus 7 is 4. So the y-coordinate of the vertex, which we've been calling k into that formula, is 4. So here is our general form, is our standard form, or the vertex form. Now, what is the a value? A is the same a I have here, so therefore a 3. X minus the x-coordinate of the vertex, we found it to be 1. K is 4, so the y-coordinate of the vertex is 4, and that's what goes there. So here it is. This is the quadratic function now written in vertex form. So really with this form here, you can immediately graph this function. Okay, and the way we would graph this function is that we would go to 1, 4 for the vertex. A is 3, so I'm going 1 unit to the right and 3 units up. 1 unit to the left and 3 units up, so we would know how narrow this parabola is. And there you go, I would graph it right there, done. So if we know the vertex and this a value, in other words, if the equation is given in vertex form, then we can immediately graph this parabola with no problems. Okay, let's try this again. All right. So all I want to do is find the x-coordinate of the vertex. B is 7. A is negative 5. So I'm just going to say 0.7. Or you can write 7/10, no problem. Or you can write 0.7, so use a fraction, use a decimal, it doesn't matter. The y-coordinate of the vertex is negative 5 times 0.7 squared plus 7 times 0.7 minus 1. So this is why I have this written rather as a decimal, because it makes it maybe easier to enter in the calculator. So I have a negative 5 times 0.7 squared plus 7 times 0.7 and then minus 1. So the answer is 1.45. Okay. So therefore this function can be rewritten as a, so negative 5, x minus the x-coordinate of the vertex, so 0.7 squared, plus the y-coordinate of the vertex, which is 1.45. So same thing. We can easily graph this function now. Okay. So let's try this one more time. I'm asking you to find the vertex, the x-axis intercepts, and then use them, and maybe the y-intercepts as well, and use them to graph this function. Okay, so a few things. I want the intercept, I want the vertex. So this equation is given to us in general form. So therefore, the x-coordinate of the vertex is negative b over 2 times a. Again, b is a negative 6. A is a 1. So that's going to be a plus 3. The y-coordinate of the vertex is what I get if I plug in this 3 into my function. So that's going to be a negative 1. So far I know that the vertex has coordinates 3, negative 1. There you go. I could immediately just go on and graph it, but I'm just going to find the x-axis intercept. So show you why we also solved those quadratic equations earlier. So first things first, if I plug in a 0 for x, I'm going to get an 8. So the y-axis intercept is going to be at 0, 8, somewhere here. But this is a good one. If I make y equal to 0, then what I end up having to do is solve this quadratic equation, right? So set the function equal to 0. And hopefully we can factor this one. If not, we could use the quadratic formula. But numbers that multiply to 8 and add to 6 are 2 and 4. Minus and a minus. So therefore, the two solutions are x equals to 2 and x equals to 4. So we do have two x-axis intercepts, as there should be two solutions to the quadratic equation. And of course, if you actually think about it, this should very much make sense, because what is our a value? Our a value is a 1. So from the vertex, you would have to go 1 unit to the right and then 1 unit up. So this is how narrow the parabola is. Okay. And there is its graph. Okay, so either way, with what I was explaining to you earlier about how A shapes the graph and how easy it is to find the vertex. But we put to good use solving quadratic equations, which we practiced at the beginning of this chapter. That's also very helpful as well. Okay, so let's state the domain, which is all real numbers every time. The range, as you see now, we're starting at the lowest value of negative 1, which is the y-coordinate of the vertex, and we go up to infinity. And then the axis of symmetry, which I don't want to write so much, so we can call it AOS, axis of symmetry, is the vertical line x equals to 3. So it's always going to be this vertical line, so therefore its equation is always x equals, and the x that it equals to is the x-coordinate of the vertex every time. So in other words, this graph has to be symmetrical about this line. So it looks the same way on the right and on the left side of it. All right, let's try this again. Find the vertex and the x-axis intercepts. So negative b over 2a, so that's negative 1/4. The y-coordinate of the vertex is what we get if we plug in negative 1/4 into the function. So if I put this in my calculator, which again, it would actually be maybe easier if I used 0.25. for it. Yep, so that's going to be a negative 5.625. So the vertex has coordinate negative 0.25 or negative 1/4. And in my calculator, I got a decimal, negative 5.625. Okay. All right, let's put it up. So somewhere down here. Okay. Actually very, very close to the y-axis, 1/4. Okay. Let's find the x-axis intercept. So in other words, let's set the function equal to 0 and see what we get. So hopefully, again, we could factor this. I did try and pick them factorable for you. So negative 3x plus 4x gives me the positive 1x in the middle. So in other words, we factored correctly. If you can't factor, remember, you can always use the quadratic formula to get to those answers. So the two solutions here are that either x plus 2 is 0, which makes x a negative 2. So in other words, we have the point of coordinates negative 2, 0 on the graph. And then 2x minus 3 is 0. So if I solve this, add 3, divide by 2, I'm going to get 1.5. So I have the point of coordinates 1.50 on the graph. They're very much symmetrical. In other words, same distance away from this x of negative 1/4 that we got for the vertex, right? That opens up. We could find the y-intercept. That's down at negative 6. Yeah. The slope is go 1 to the right and then about 2 up. So, yeah. All right, and there it is. So now we're going to practice these problems. Let's go backwards and find the equation of a quadratic function given certain information. Again, that's very much equivalent to what we have learned back in when talking about lines in chapter 2. We looked at it forwards, backwards from every point of view. Given the equations, we can find the slope, we can find points, we can find intercepts, set them equal to 0, find the intercepts, graph the line, find the slope. However, we could also have gone backwards, given the slope and the intercept, or given 2 random points. Can you find the equation of that line? And every single time we use the slope-intercept form of it, because it was much easier to get to the equation of the line that way. Same thing here. When I want to find the equation of a quadratic function, I will simply want to use the standard form or the vertex form. So the a times x minus h squared plus k. All right. So find the equation of a quadratic function. There I go. Given the vertex is at negative 1, 3. That means this is the h value. This is the k value. So k is 3 and h is negative 1. So x minus minus 1 plus 3. So far, I replaced h with a negative 1 and k with a positive 3. To find this equation, I still need a. Let me write this down. We still need a. Okay. Okay, what else do I have? I have a point, a different point, an extra point. Really, to graph a parabola, a quadratic function, all you need is the vertex and one extra point. That's it. So the point is 0, 7. That means what? If x is 0, y is 7. So in place of f of x, I'll put 7 because remember, that's your y. And in place of x, I'm going to put 0. And the only missing thing now is going to be the a. 0 plus 1 is 1. 1 squared is 1. A times 1 is a. So therefore, minusing 3 from both sides of the equation gives me that a is 4. So here is my quadratic function. You can write y equals, but a is 4, h is 1, and k is 3. That's all I need. Okay, so let's try this one more time. Same, find the equation of a quadratic function with a vertex 2, -9. So immediately I will go and I will, in place of h, write 2. In place of k, write -9. So there you go. I'm more than halfway through, okay? Still need a. So to find a, what do? I plug in this x and this y into this function. F of x, remember, stands for y. So instead of y, I'm going to write 5. A is really what we're trying to find. 4 is x. Okay. 4 minus 2 is 2. 2 squared is a 4. So to solve for a, I'm going to add 9 over. And then divide by 4. So you can leave it as 14 over 4, which, by the way, has to be reduced to 7/2, or you can write 3.5. Either way, it doesn't matter which form of it you want to use. But here is the equation of this quadratic function. Okay. All right. Here I'm giving you a graph this time, and we want to see what the equation of the parabola is. So same way, can we find the vertex? In these problems, it was given to us. We are now given the graph. However, can we read the vertex easily? Here's the vertex. The x-coordinate is -2. The y-coordinate I see is -3. So far, this is my quadratic function. A times x minus -2, so plus 2, plus k, and k is a -3. Okay, and now we can find a. So grab any point. It could be the y-axis intercept I've given you in this problem, any random point in the second problem, it doesn't matter. Is there any point that you kind of see exactly going through corners? And right here I see the y-axis intercept at x is 0, y is -1. So we can use this for an x and the y. So 0 plus 2 is 2. 2 squared is a 4. Add the 3 over. So remember, you still have to use the order of operations. To get to a, you would add the 3 over first. Then divide by 4. You can't do 4 minus 3, even though they're temptingly close because this 4 is part of a multiplication. So it has to be multiplied to A, and we can't minus the 3 from it. So A is going to be a half. The way I see it. So here's my function equation. 1/2 x plus 2 squared minus 3. Okay. And here are the couple applications I have for you. Oh, or maybe more than a couple applications. Let's go through them really quick. So what are quadratic functions? It says, suppose that the price per unit in dollars of a cell phone production is modeled by, so again, this is the price per unit where X is in thousands of phones produced. So the price of an item very much depends on how many items we're selling. So we're always more willing to go down in price if we could sell more items. It's like buying in bulk. So it says, and the revenue is represented by, the revenue is always really the number of items sold times the price per item. So it very much makes sense if you bought, I don't know, 3 t-shirts at $15 each, you paid 3 number of items times $15 an item, $45 total, right? So that's what the revenue is, how much money in total is being made. So for our function right here, as you see, that's simply x times 45 minus 0.0125x. So if I distribute this, I'm going to get 45x minus 0.0125x squared. So as you see, this revenue function is a quadratic function. Yes. And what's very important with a quadratic function is that it has a vertex. So anytime we're talking about an upward-looking parabola, the vertex is the minimum point on the graph. If, look, minimum, lowest point on the graph, lowest point on the graph. If the parabola happens to be upside down, the A value is negative, and the parabola opens upside down, then you will have a maximum point on this graph. So the vertex is a min or a max, depending how the parabola opens. Yes. So if I look at this function, so again, to find the minimum or the maximum really means to find the parabola's vertex. I have this a little backwards here for you, but if I put it in order as start with the x squared term, I hope you notice that your A value is a negative number. So remember what I said, if the A value is a negative, then the parabola will be opening down. So therefore, we will have a maximum point at the vertex. So either way, when we say maximize or minimize a parabola, means to find the vertex. All right. How do I find the vertex? Well, the x-coordinate of the vertex is negative b, which for us is 45, divided by 2 times a, which for us is negative 0.0125. So let's put this in the calculator, and I'll put it in mine. So 45 divided by 2 times 0.0125. So I got 1,800 positive. Okay. Now, what we're interested, find the production level that will maximize revenue. So the production level that would maximize revenue, we didn't ask for that maximum revenue. It's just the x-coordinate of the vertex. So x is in thousands of phones produced. So produce 1,800,000 phones, and that's where you'll get your maximum revenue. Okay, that's it. So we'll try a couple more. See, maximum will mean we're finding the vertex. This time, the function is given to us. So as you see, it's a parabola. A is a negative value. Therefore, the parabola will be opening down. Therefore, we will have a maximum point at the vertex. Okay, so to find the x-coordinate of the vertex, we use the same formula. Our b is 229. A is negative 4.9. There's your b. And put this in your calculator. 229 divided by 9.8, which is 4.9 times 2. So that's about, I'm getting a decimal value. 23.37. I'm going to round this off. Okay. Now, we're not asked it again. I didn't even read the story. It says a rocket is launched in the air. Its height in meters above sea level as a function of time. So t is time. So our x value is time. Our y value is height. So the reason why I'm saying this is because am I looking for the x-coordinate of the vertex like the problem before, or am I looking for the y-coordinate of the vertex? So this time we're looking for the y because it says what is that maximum height. So all I have to do is plug in this value I got before, this t, which is the x, and put it in. And again, it's going to be an approximation, but that's what we're going to put in our calculator to come up with the answer. So the maximum height of this rocket. So here it is, negative 4.9 times 23.37 times another 23.37 plus 229 times 23.37 and then plus 234. So the maximum height in meters, as the problem says, is about 2,909.56 fine meters. If you round it a little differently, you might have gotten slightly different answer. Don't worry about it. The point is, again, anything that's launched up into the air, up, yes, what's going to happen to it? Eventually, gravity gets a hold of it and it gets pulled down the same exact way. So anything that goes up follows always the path of a parabola. In other words, the way it goes up, the same way it's coming back down. So it's always going to be symmetrical about this maximum height is about to reach at the vertex, and then it's going to come back down and strike the ground. Okay. So the same thing here. I'll tell you the story with this problem. It says a ball is thrown into the air from an initial height of 80 feet. So at time 0, the ball is at 80 feet high, and it's thrown into the air with an initial velocity. It says the path that the ball takes follows this parabola. And again, as you see how it's a negative a value in there. So in other words, it goes up, and then it's going to come the same way down, and then strike the ground. So we're looking at height versus time. Okay. So one more time, what is the initial height of the ball? So what's the height when the time is 0? It did tell you actually in the story But as you see, that very much shows from the equation as well, because at time 0, if you plug in 0 for t, you're going to get 80. So in other words, really that's where the 80 comes from in that equation. The second question of the problem is how long, so how long, that means what is the time it's going to take for the ball to reach the maximum height. So in other words, what I'm looking for is the x coordinate of that vertex, because the maximum height is going to be at the vertex. So our x value is called t in this problem. So that's negative b, and b I see is 64, over 2 times a, and a I see is negative 16. So when you put this in your calculator, you're going to do 2, and these are seconds. So it's going to take 2 seconds. The ball is going to reach the maximum height, and it's going to start coming down. The next question is, what is that maximum height? So in other words, what is the y coordinate of the vertex, right? So that gives me the y, the height is the y for this problem. And what is the y coordinate of the vertex? So again, to find the y to any x, we just have to plug in that into the function. So I'm going to plug in 2 into the function above. So negative 16 times 2 squared plus 64 times 2 and plus 80. So that's going to be negative 16 times 4 plus 64 times 2 and plus 80. So that's 144 feet. So in other words, it's going to take 2 seconds for the ball to go from 80 feet up to 144 feet. And then the ball is going to come down to the ground. The next question is interesting. It says when. So again, we have to find a time. When will the ball strike the ground? So when does it reach here? Well, the ball strikes the ground. That means the height of the ball has to equal to 0. Yes? That's what it means to strike the ground. The height is going to be 0. So what we need to do is solve this quadratic equation. Find the time it takes until h is going to equal to 0. So let's see if I can factor this one. I'm not so sure, but if I can, 16 might be a common factor, and that's going to be 4 times. And 16 goes into 85 times, so that's actually pretty nice because we can factor this trinomial. So numbers that multiply to 5 and subtract to be 4 are 5 and 1. So one possible answer is t is 5, and these are 5 seconds. And the other option is that t is negative 1, but that's not going to be an option because time cannot be negative. That's really the value that's behind the 0, but time is only positive, so we're moving forward. Therefore, it's these 5 seconds right here that we are looking at, right? The negative one, yes, if I solve any random equation with no meaning, quadratic equation, I'm going to get 2 answers. We do not want the negative 1 answer, okay? Makes no sense for this problem. All right, so I know this was a long section. That's because there's a lot going on.